one, and we are recording today's lecture on lipids. Okay, so some of the things that I'm going to introduce to you today that you will see, maybe not so much in dentistry, but certainly when you get checkups or when you hear about it, or if people on anti-cholesterol drugs, are the terms of high density or HDL lipoproteins and low density lipoproteins. And that is something that we will delve into tomorrow and see why HDL is considered a good fat and LDL is the one that you want to minimize in your diet. Okay, chemically, why that happens. Okay, so we're going to start today with looking at the classes of the lipids. Okay, get you some, as always, start you with a bunch of terminology that's going to sound kind of foreign to start with, but you'll get more and more familiar with it. And looked at condensed structural and but mostly line angles, the little zigzag things indicating carbons, because there are so many carbons in the carbon change in lipids. It's just way, way, way faster to use the line angle drawings, be able to draw those. And look at things like phospholipids. That should ring a bell about phospholipid bilayer when we're looking at cell membranes. We'll take a look at those a little more closely, other than just, maybe you remember a hydrophilic, hydrophobic area, and they make cell membranes. I wouldn't expect you to remember a whole lot more than that, but we'll go into why that actually happens. And then we'll look at steroids. Steroids are actually a lipid. Okay, I mean both the sex hormones, male and female, testosterone, progesterone, estrogen, as well as mineral corticoids are also steroid lipids that all start with cholesterol. So cholesterol isn't necessarily a bad thing. You do need cholesterol to make steroids, amongst other things. Okay, mineral corticoids like cortisol, hydrocortisone, those types of things. Okay, and well, like I said, we'll look at the lipid bilayer. Okay, so lipids are biomolecules, I'll just read this for you, that contain fatty acids or that's the important part, or a steroid nucleus. When you have a steroid nucleus shown here, which has 3 hexane rings, 6 carbons, and 1 pentane ring. Okay, those are the 4 rings that are in every steroid. Okay, and comes from the Greek for lipos, for fat. Okay, for obvious reasons, hopefully. And we'll look at the classes of lipids. First of all, okay, so where we start with here is the following. So we have lipids in 2 major classes, and there are subdivisions we'll get back to. We have the fatty acids over here, and it's like a family tree of lipids. Steroids over here, steroids over here. Okay, and fatty acids have that structure. It kind of looks like something, one would have a long tail, like a long fish, but you have this long tail of carbons attached to our carbonyl group, which we touched on. Carbonyl, we saw the ketone, aldehyde, that's an example of other carbonyls. The one that you see a lot in lipids is the following, with a double bond on one end to an oxygen and a hydroxyl, and that's called a carboxylic acid. Carboxylic acid, indicated by this carbon and those 2 oxygens right there, oftentimes abbreviated as carbon, that carbon, oxygen, oxygen, and then that hydrogen corresponds right there. So you see oftentimes something like boom, 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 boom. That's all of the carbon change with a COOH. And there you have a fatty acid, an example of a fatty acid. Okay, and steroids, like we mentioned, They all start with that 4-carbon ring, the 3 hexanes, and the pentane. Okay. Now to further subdivide, we have the fatty acids. Let me clear out a little more room here. Boom, boom, boom. Ooh, I don't want that. How do I make that go away? There we go. Clear my fatty acid with carboxylic acid, and under fatty acids, there are, furthering that family tree, waxes, triaglycerols, glycerols. Okay, we'll get into those. Those are our 3 fatty acids connected to something. Tria, and glycerophospholipids. Okay, that may or not sound familiar from looking at membranes, but glycerol and then phospholipids. Lipids. Okay, there we go. And you'll see that PO4 in purple, a little circle, that's the phosphorus part of phospholipid. Okay, and what do we have there? Oh, there's Alejandro. Have the glycerol phospholipids that you saw when we were looking at cell structure, cell membranes, and sphingolipids, which I'm not going to really delve all that much into. Okay, they only got so much time, life, and so much room in everyone's brains to get through in a couple of lectures. But I do want to give you some actionable information, as well as some familiarity. So if you go to the grocery store, grab one of those cans and we'll look at monounsaturated, polyunsaturated, cholesterol. All those things are going to have a lot more meaning after you look at this, and will help you long term, hopefully, with your diets and heart health throughout your lifetime. And then steroids, of course. I could easily teach an entire course on steroids of various types, but for now, just keep that ring structure, that ring backbone in mind after we get through the fatty acids, and we'll spend some time with steroids. Okay. Okay, lipids. Which type is described by the following as a fused 4-numbered ring system? That's a steroid. Long carbon change. Okay, those are your fatty acids, and carbonyl groups also fatty acids. Although there could be carbonyl groups on the steroids as well. To be honest, kind of a misleading question. And which would not be a characteristic of lipid, may contain carboxylic acid. We're always established that it can be. 4-ring structure in steroids, soluble in water, and mostly nonpolar. So another characteristic of fats, and you'll see this if you try to float a fat canola oil, cooking oil in water, it will not dissolve in the water, it will float on the surface. So that means that fats are non-polar. Okay, if they were polar, they would dissolve in the polar solvent that is water. So they are non-polar. Okay, and are not soluble in water. Okay, so they are not soluble in water due to them not being polar. This is kind of a useful visual. When we're looking about why fats cause the problems that they do, clogging up coronary arteries, clogging up carotid arteries, causing strokes, heart attacks, all that kind of stuff, it's due a lot to how they fit together based on the structure of those tails on the fatty acids. So some of them stack together like nice Pringles if they can get in a can, right? You can get a lot of Pringles in a can because they fit together very, very nicely one on top. But there are another form of fatty acids, the unsaturated, monounsaturated, and polyunsaturated, that do not fit together because those tails on the end have kinks, and so they don't fit together. And if they don't fit together, they are less prone to clogging things up and forming this real hard mass. Okay. Okay, so fatty acids. And we looked at our fatty acid family up here. Let's get rid of steroids, and we're going to look at fatty acids right over there. Okay, so they typically have that carboxylic acid on the end with a carbon chain that is, 12 to 18 long. What I got there: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so I'll put this up. That could be a fatty acid. Okay, they're insoluble in water, nonpolar, and here's the key that I want to drill down on a little bit. If they are saturated, they do not. None of these bonds, none of these carbon-carbon bonds in the tail are double bonds. Okay, they are saturated. Okay, and those are bad. Those are bad bonds. Okay, and unsaturated, just like it sounds, have at least one carbon-to-carbon double bond somewhere in the tail. Okay, it can be one or more and then become unsaturated. And you have monounsaturated when there's only one double bond, and polyunsaturated when you have anything more than one double bond in the fatty acid tail. Okay, saturated, unsaturated, dependent on double bonds in the tail of that fatty acid with our carboxylic acid on one end. So this is what they look like if you get the condensed and the expanded, the ball and stick model. What we'll mostly be looking at is this line angle, just because who wants to draw CH2 12 times, 15 times, 20 times, okay? So it's just our line angle formula to indicate that carbon chain. And you can see that one is saturated. There are no double bonds there in that carbon chain. Okay, so some examples of saturated, meaning that they only have carbon-carbon single bonds in the carbon chain. To reiterate, right there. Okay, only have carbon-carbon single bonds. Well, we're calling those alkanes, but in here, it's the same concept, carbon-to-carbon single bonds only. Yes, they are an alkane, but we call that fatty acid chain as being saturated. There's no double bonds. So you should recognize some of those. So coconut oils, palm oils, a lot of the fats that you find in animal are saturated. Okay, and if you know, those are the ones that are solid at room temperature. I mean, you get a nice steak, the marbling in there. That's primarily now you know that they are saturated fatty acids for the most part. Okay, and they're all stacked together, they're packed together. All of these carbon tails just packed nice and neatly on top of one another. And that is why, and they stick together and they form that sticky mass at room temperature. And there's our carboxylic acid on the end. Okay, this is a whole bunch of fatty acids all stuck together. It's coconut oil or in your steak, palm oil. All right. So things that are stuck together at low temperature, think about it. That's bad. It's going to clog up your plumbing, essentially. Stick to the inside of your vessels. So a monounsaturated fatty acid, let me drop one here. So I have a carbon tail. I'm just going to stop there. Does have that carboxylic acid on one end, but monounsaturated. has the following feature. It has one carbon-to-carbon double bond somewhere in that chain. I'll just stick it right, it could be anywhere. I'll just stick it right there. Okay? That causes a kink in that chain, so they no longer stack on top of another like we did with the saturated. So now that you have a kink, this is like, they don't stack, they don't stick together, and they are much more fluid and at lower, much more fluid at room temperature, essentially. So it's found somewhat in butter, but in olive oil, monounsaturated olive oil, it's liquid and doesn't tend to stick and cause those problems with clogging of the arteries. And then you get a clog in the artery, you get inflammation, and you're often running with coronary artery disease or clogged carotid arteries, and you can throw thromboses, or the thromboses can then embolize and then cause all the problems that we get. Okay, and the last fatty acid tail we'll look at is the polyunsaturated. So you can probably see where I'm going with this. Pretty straightforward. We have another fatty acid chain of some sort, usually longer than that, but I'm going to quit there. Carboxylic acid, and we have at least 2, but you can have 3, you can have 4. You have poly or anything more than the 1. And that's things like soybeans, safflower, sunflower, corn oil, those types of things are definitely flow more freely, don't stack together, don't cause all the problems that the saturated fats do. So the saturated fats, if you look at your can of whatever, what do you buy? Buy a gallon of milk. It'll give you the amount of saturated versus unsaturated and how much of that you should be allowed, according to the FDA. Okay. That gives you some idea of the problems that saturated fatty acids cause. Okay. And really quickly, and this is something that we never really got to. I do want to address it right now because who knows, it might come up. When you have a double bond in a carbon chain, okay, you create a situation where you have sides. So if you can have a hydrogen going down, or you could have something going up that way. In this case, both of these are on the same side, so that would be called a cis version of that isomer. Okay. And cis and trans. I know we've heard about this on in other ways of talking about people's orientations and whatnot, but it also has a specific chemical meaning, cis and trans. So if you flip that over, so you have your alkyl groups, carbon groups, side chains going off in opposite directions. If they switch from the top to the bottom at the double bond, it's trans. Okay, cis, they're on the same side. Okay, they don't switch. Trans, you switch at the double bond. Okay, and those kinks, all of these kinks, double bonds, and those fatty acids can assume either the cis or trans configuration. Either way, it's not a nice straight line, and it makes it really hard for these fatty acids to pack into each other and get attracted and form an insoluble glob of fat. So cis and trans, that's actually a fairly important concept. Okay, so you probably heard about essential fatty acids and non-essentials. So the human body is capable of synthesizing a lot of the fatty acids. We take in our carbohydrates, you eat a potato and a bunch of rice, and you can make some of the fatty acids you need. There are some that you need to get in your diet because you can't make them for proper functioning. Okay. So, like a lot of the polyunsaturated that you get from polyunsaturated, we're looking at soybean, safflower, sunflower, corn, polyunsaturated. Some of those things, so where's oleic? No, they don't show oleic. Monounsaturated. Oh, yeah, linolenic. Sorry. Yeah, there we go. Linolenic acids, linoleic acids. Some of the stuff, they are essential fatty acids. You can't metabolize them, but you can get them very easily in some of the polyunsaturated cooking oils, for instance. Okay. And that's what makes them essential, is because you can't metabolize them, you have to take them in. Okay, so here's a visual representation of my scribbles that I did. This looks a little bit cleaner, I think. So when you have the saturated fatty acids, notice they are stacked like a pile of lumber, right? Or a can of Pringles, like they said, and has a very high melting point because all of these bonds, molecules are attracted to one another. It's hard to break them apart, and they form a very insoluble glob in the wrong places sometimes. And it comes all the subsequent issues that we have with coronary artery disease, primarily. Okay? And there we go. And then just to reiterate that point, when you have monounsaturated and polyunsaturated fatty acids, they don't cause the same problems because they are not stacking together and forming this insoluble complex of fatty acids. Okay, so let's just kind of check if you ever have a fatty acid that comes up. It's an acid because it has a carboxylic acid out here on the end. Total carbons, we have 1, let's see, 2, 3, 4, and then 7. They just, instead of drawing CH2 7 times, there's 7 carbons, another 7 carbons. So 1, 2, 3, 4 plus 14, 18 total carbons. Okay. Is it saturated, monosaturated, or polyunsaturated? This is monounsaturated. There's only one carbon-to-carbon double bond. And it's likely to be a solid or a liquid, probably a liquid, okay, because it's not packing together. And of course, would not be soluble in water because fatty acids are nonpolar and are not soluble in water. Okay. Carboxylic acid, 18. Make sure I did all this right. It is a liquid and it is not soluble. Okay. Okay, so I am going to touch on, how deep should I go? Maybe through omega-3s, because that is something that you probably all heard of as something that's good for you. But we'll start with prostaglandins. Prostaglandins are hormone-adjacent, hormone-like substances. They don't circulate per se, but they're like localized hormones. I don't know if you remember me mentioning that in A&P, but that's what they are. Okay, they come from arachidonic acid, which is a polyunsaturated fatty acid. Okay, fatty acid with 20 carbon atoms with several carbon-carbon double bonds in its fatty acid chain, or its carbon chain. Okay, also called the icosanoids. Okay. They do a lot of things: blood pressure, contraction of the uterus, relaxation of the uterus, but probably the big thing that we all experience with prostaglandins is pain. Okay, so in this situation, someone banged their finger with a hammer and they've caused some local damage to some tissue. When that happens, some of that arachidonic acid is released from the damaged tissue. And that's what arachidonic acid looks like. Yeah, okay. And the painkillers that we can take, aspirin, ibuprofen, naproxen, Relafin, blah, 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 all of those, non-steroidal anti-inflammatories that you've heard mentioned and that you will see every day as a dentist, this is where they're working. They are blocking, I'll just write arachidonic acid right there. So we have the blow of the hammer. Let's see. Yeah, I give myself a little more room. So tissue damage releases arachidonic acid, and there are a series of enzymes that convert arachidonic acid into these PGF. But essentially what happens is molecules that induce everything that goes with tissue damage. Pain, you feel pain with those. You get inflammation, redness, all of that stuff. Okay, and they can even be fever-inducing. But for today, pain and inflammation are the main thing. What ibuprofen does and aspirin, aminosalicylic acid, is they interfere with this enzyme's ability to turn arachidonic acid into the molecules that cause the pain and inflammation. Okay, so they're pain relievers because they get in the way of the molecules that cause pain and cause inflammation. Okay, so now you know. So there's aspirin. That's what you look like, what they look like. So we should see some things that look kind of familiar here. We have benzene rings. I'm not going to expect you to know these, but just kind of pat yourself on the back for being to recognize some of this stuff. It should be starting to make sense to you, right? It's not like a completely scary thing when things come up, but benzene rings, double benzene ring for naproxen, carboxylic acids up there on the aspirin and on the naproxen, methyl groups right here, okay? And yeah, so there you go. I mean, it's just kind of cool to be able to look at things and have some idea of what's being drawn. At least I thought it was cool back in the day. You might not be nearly as impressed with that as I am, but I think it's cool. And it's my class, so there you go. Okay, so omega-3s, so the things you find in fatty acids, the fish oils, you've probably heard how awesome omega-3s are for you. So let's take a little closer look. So unsaturated fats are more beneficial than saturated fats. So unsaturated, good. Saturated, bad. Okay. And so there are omega-6 fatty acids in vegetables. Okay, and what that means, that's just locating where the first double bond happens from the end. So 1, 2, 3, 4, 5, 6. There's that first double bond. So we have a polyunsaturated fatty acid with the first double bond occurring at carbon 6. That's all that means, okay? And there's, arachidonic acid, of course. We just saw that when we were looking at the prostaglandins and the pain relievers. So omega-3, you can probably figure that out. Yeah, so omega-3s, so omega-6s, vegetable sources. Omega-3s, awful lot in fish, so especially cold water fish, lots of omega-3s. Another polyunsaturated fatty acid, carboxylic acid out on the end, but the first double bond occurs 1, 2, 3 carbons in from the end. 1, 2, 3, 1, 2, 3. That's what makes them omega-3. 3. It's just the placement of that first carbon-to-carbon double bond. Okay. And so there are various omega-3s, linolenic, eikosapentaenoic, and docosahexaenoic, DHA, EPA, ALA. And that's if you go and grab a bottle of omega-3s, you'll see, and if it's properly labeled, the ALA content, the EPA content, and the DHA content. Those are just various fatty acids that are polyunsaturated fatty acids with a double bond at the third carbon with various lengths of carbon chains coming off of that carboxylic acid that's all the way off on the right. Okay. Kind of cool. So now you're not flying blind when you're taking their supplements. And I'll remind me to ask tomorrow if anyone's taken omega-3s. Okay. So they can help with atherosclerosis and heart disease because here I've been kind of drilling down on cholesterol forms the plaques that adhere to the walls of the blood vessels, and blood vessels get smaller, so less room for blood flow to squeeze through. Blood pressure goes up to compensate for that, and as more plaque forms, you can get a blood clot because it's not nice and smooth, and clotting factors can get activated and cause a thrombosis and embolus. Okay, and omega-3s lower a couple of things. Number one, they don't stick together. Number two, they do lower the ability of platelets to stick together. And the platelets are the things that will stick to a cholesterol plaque and cause an embolus. All right, I think that's a pretty awesome place to start. Kind of a bit of fun information. Does anyone have any questions about that? Okay, so let me